Lambda Networks transform self-attention. Is Lambda Layer similar to self-attention in a transformer? What gives LambdaNet its power? LambdaResNet beats EfficientNet, but does it lose to a performer transformer? I will answer these in this video, and as well, just before I start, I will give you super fast summary, the juice of the paper. So if we write down equations for both Lambda network, Lambda layer, and attention, we can see what are the differences. In both cases, the query matrix is completely on the left, value matrix can be placed completely on the right, and we have something like K matrix in between. However, in attention, we have a softmax applied to both Q and K, but in LambdaNet, we have one part which doesn't give it much performance, which uses softmax but applied directly to the key matrix. And then we have a second part from which majority of the power comes from, these positional embeddings. There's no softmax there. This is sort of like learned attention key without softmax. And as well, it does not actually, it's not two-dimensional matrix, it's actually three-dimensional. So you will ask, how the hell do I multiply these? I will show you. So Lambda Network, why we are talking about it? Lambda Network achieved state-of-the-art when it was suited on a decapitated ResNet 50, outperformed EfficientNet, and vanilla transformer with self-attention heads. LambdaResNet also achieves 4 times speedup over EfficientNet at same accuracy. So in the paper, they present this graph where you can see a comparison. It's a graph on y-axis, it has accuracy. On x-axis, it has a training latency. And here we can see that for same accuracy, the top one accuracy, the LambdaNet is much faster. It has much lower training latency. The issue is that it still suffers from time-space complexity with the sequence size, which is why I think Relu-Performer could overtake it in future. What is Relu in Performer? So I have a video on YouTube about Performer. It's called Performers Favor Faster Transformer Attention. And it explains that the performer is a little bit similar to LambdaNet, and I will mention it once more. So classical vanilla attention has this attention matrix. This is created multiplication from the query and key and softmax, and that one is L times L. And what performer does is that it transforms each of these query and keys separately, and and introduces special dimension M, and once this is done, the complexity reduces to linear complexity, and as well the approximation of the softmax is very good. It behaves very much like attention. And the trick they did kernel approximation, and in the end they actually found out that if they actually replace exponential in this kernel approximation with Relu, they get even 10x speed up for last computation of exponential is 10 times, maybe more. Do you know? Let me know. Faster than softmax than Relu, right? Slower than Relu. All right. So you can have a look there as well. Okay. So let's get back here to the Lambda networks. We are back in the Lambda networks. So the majority of the model's performance, and this is the interesting part, where do you think it comes from actually, right? So you have, what can you choose here in this orange equation, you're right, it comes from these embeddings actually. And this actually weird softmax, this is applied only to keys, actually it doesn't contribute very much. Yes, this is the three-dimensional embeddings. That's where the performance comes from. So these position embeddings, this E matrix, are used sort of as a key matrix in the self-attention in sort of similar way, right? Without the softmax though. Then these embeddings as well are trained, but they are not dependent on the input. So normally the key matrix is actually linearly dependent on the inputs, but in this case it's not. It's sort of static. So in that way you get a speedup that for the whole page you can have one common embedding this three-dimensional matrix. And that's the trick here, is that for each output position there is a separate key. This is what we don't have in self-attention. In self-attention we sort of share keys. I will show you. But here we have, thanks to the extra dimension, we have a separate key for each output position. In self-attention, if self-attention is a sort of querying of a key value store, right? Because we take keys, we match them with queries, and those queries that match a lot, those are highlighted by softmax, and then we take values from those results. So if self-attention is this, then LambdaNet is actually a differentiable querying of a pattern value store. So by pattern here, I mean these position embeddings. These are sort of static, common things. We don't have these keys that change, we have these patterns. How are Lambda networks actually similar to self-attention? So there are some similarities and as well additional analogies to the performer that I mentioned. And I will satisfy your first foreknowledge here. So listen on, friend. In following, the big X will denote input sequence of a dimension n times d, when n is a dimension of an input token count and d is a token embedding dimension. The interaction and attention context is the entire input sequence here for simplicity. So in the paper, in the Lambda Networks paper, they are forced to actually reduce the attention context to just 23 times 23 pixels, which is a very small image patch, right? You would like to actually have global attention ideally, but you can't compute this because Lambda layer is squared in complexity in the input token count. Big issue. And that's why Relu-Performer could outperform, because it is linear in the input token count. So how does it actually specifically looks like? So we have a query matrix that's created by multiplying W with X, which X is input matrix, and this query matrix is n times K, and K is less than D usually, or something similar to D, but not exactly D. It's some other dimension. Then we have a query vector, which is just a slice along the position dimension. Then have a key. Key is again a linear. It's W matrix applied to X n times key, right? And we have a value W matrix applied to X n times D. All right. So far, this is very similar to the transformer, except for these keys, this K dimension. But here it comes. Positional embeddings are denoted by E, and they are n times K. So this is the three-dimensional matrix. It's squared in n and plus K dimension. So squared in n, right? So here the complexity comes from here, and the performance also comes from here. For each two positions in the input sequence, there is an embedding vector of size k. They also introduce translation-invariance. This is excellent for images, by storing the embedding vectors in a translational invariant, that is, relative format. Softmax applied along the n dimension is denoted by sigma. Softmax serves here to strongly prefer a select few of the value vectors indexed by n, right? But it's applied actually only to key. However, as I mentioned here, the selection factor here is a logit. It's not the key query match, the dot product, as I mentioned before. We do the softmax on the key vector itself is the softmax. We sort of are saying, okay, so this key needs to be heavily skewed, sort of normalized, that it only highlights some values. And also, I think that's the reason why it doesn't contribute that much, this part. The embedding, position embeddings actually do a lot. The paper itself is written in very unfamiliar form. I think that's because the authors come to this conclusion from a very different angle, but I think I did a good job at rewriting this into a format that is very similar to attention. So in this equation below, on the left side, you have the format sort of similar to what is in the paper, and we do transpose to that. What's important here that we index by L, which is effectively an output dimension. So this is some sort of one output position. This lambda is sort of like linear function. It sort of comes from functional programming, but that's not important. And so if we rewrite the equations they have there, we will get we will have this query vector which only has a k dimension, and we do multiplication in k dimension with this matrix. So here we have a softmax on key matrix plus embeddings, and only in the one specific slice for the output, for the specific output index, right? And then we multiply by positional dimension to V matrix. So these subscripts, as you notice, denote along which dimension we do the multiplication. And you can remove those and sort of simplify it in this format, that Q multiplied by brackets, softmax K plus embeddings, position embeddings, close bracket times V, but it's not completely correct. The correct way to look at it is this visualization. So we have some output, n times d, that's the same in the attention as well. Then we have a query matrix n times k, and that is multiplied, and you can see that it's sort of rotated, this matrix. That's because, as I mentioned, we have this indexing on the embedding matrices, so we have this third dimension, and that's why I draw it like this. So we have this Q, and that multiplies in this sort of horizontal plane with these slices of the embeddings, and the embedding matrix is n times k, and then here comes the value matrix is n times d, and that multiplies with e, and yes, the result is n times d. While in the softmax attention, in self-attention, we have the sigma applied to n times d, that's the q, and then we have a d times n, this is the key matrix. We apply softmax to that and apply it to value vectors. So self-attention, much simpler. It makes very good sense. This Lambda networks doesn't make as much sense, a little bit too complex, but we don't know yet. I think that this self-attention with extra speed up, I think it will outperform outperform this, especially because of the linear complexity introduced by the performer. All right, so I hope you got sort of insight into Lambda Layer, because now I will compare it once more to the self-attention. So to be fair, right, we have to mention that in transformer we also have a positional encodings, which are also positional embeddings, which are learned, and they are actually added to the input. So everywhere here in the Q, K, and V, we just add a P to the inputs, and then we transform. And the self-attention, as I mentioned before, softmax to Q and K, and that as a whole times V. Performer, what is this cool performer thing? As I mentioned, the performer does this, has this kernel function that approximates softmax, such that if you use this function, you can actually calculate approximation of self-attention in this way, and you get linear speed. It's great, and they have many tricks over there in performer. It's not as simple. They actually introduced some, they made a little thinking over there. How is LambdaNet doing in the space and time complexity? First, in terms of complexity, is vanilla transformer self-attention. As I mentioned, it's squared in time and space because it materializes the attention matrix, and it does it so for each patch input. The second place takes the Lambda layer because for the whole batch you have this n squared complexity only once to calculate. But the first place takes the performer. It's linear in space, and so that's great. And this why I think that's my favorite now. How Lambda layer performs compared to self-attention and performer. The paper here compares Lambda layer to transformer self-attention. While Lambda layer outperforms self-attention, it does so by only a small margin. For experimental specifics, see the paper, but here the Lambda layer is not applied to the entire picture, but only on 23 times 23 patch. And in the paper they show that they outperform self-attention, but the Relu probably will have similar performance as a self-attention, but will be linear, and you will be able to use bigger patches, and then Relu-Performer probably is going to win. Are Lambda's positional embeddings required? Absolutely. They actually drive most of the results, as I mentioned, and they tried this in the paper, and they found out that the softmax on the key part, they call it content part, and it doesn't matter that much, and the most important part are the embeddings. So the actual equation is more like Q times C, E times V, as in the infographic I mentioned at the beginning. There's one more thing, of course, subscribe if you want to see more videos like this. I sort of progress over time with you, learn more. I'm becoming more and more professional in the machine learning space. And as well, I have one more interesting thing you should consider. You can now meet other machine learning enthusiasts online and one-to-one in a video call each week. Each week you can meet an interesting person, and you can break out of your isolation in the remote work. And as well, you can also expand your horizons simultaneously and find interesting people in machine learning space. So if you join this machine learning sort of subscription, this sort of tool, you will be able to network one-on-one around your online village. And the tool is called Random Meets. You need to click here, provide email or log in with Google. And you can try it out. If you won't like it, you can leave. Also, you can subscribe by email to my blogs, and give me some comments. What should I improve? Yep, and hope to see you next time, and have a nice Christmas. See you.